Already this year, we've seen how we would make the graph of y equals the absolute value of x. It's just in this lesson, we're going to be adding in many different transformations to it and working straight from the equation rather than having to go through the function notation as well. So first up, this is our parent function, just y equals the absolute value of x, because it doesn't have anything else in it in terms of a transformation. There's nothing added, subtracted, multiplied, divided, etc. that would change it. And so you may recall that our absolute value graph, it is that V-shaped graph. And once we know that is our beginning graph, our parent function, everything else we do is just some sort of a transformation of the exact same thing. So if I take a look at this next equation, this time we're going to be graphing y equals x minus 2 minus 6. Now literally what that means is I'm taking my parent function and I'm going to be moving it. Remember, the minus 2 inside moves it to the right 2. So I'm going to be taking that entire graph and moving it to the right 2. And then the minus 6 means I'm taking the entire graph and I'm moving it down 6. So literally, it's like taking all of those points and just shifting them over and down in order to be able to get our new graph. Now notice this wasn't done using function notation, but again, when something is subtracted inside with x, it moves it to the right by that amount. And when something is subtracted on the end, it moves it down by that amount. Where you would have seen this previously using the function notation, you would have seen it written like that, but you can see here the similarities between them. And this one is really a matter of taking that jump from using the function notation to the general equation along the way. So let's take a look at another equation this time. In this case, we have negative absolute value of x plus 5 plus 1. Okay. So then, first of all, notice what the negative does. The negative flips our graph upside down. So already we know that our V-shaped graph is actually going to be opening downward instead of upward. Then the x plus 5, that's going to tell me to go ahead and shift the entire graph left 5. Then the plus 1 shifts up 1, which means that this is then that graph. Okay, next one. Now we got the number multiplied out front. And just like when we have our function notation, that number out front would mean that we're applying a vertical stretch. It's doing the same thing here. So my V-shaped graph is going to be going up 3 times as far here, and it's shifted to the right 2. And so I go over to the right 2 for my vertex, and then instead of going up 1 over 1, I'm going up 3 and over 1. So far, all of these transformations have been ones that are familiar to us, ones we have done with the function notation. But now it's time to throw in something a little different. What if that number that we're multiplying by isn't a nice pretty whole number? Like in this case, it's 1/2. Well, it still is doing the same thing. It's still multiplying your height by that number. Well, in this case, though, what does that mean? Well, our graph, instead of going over 1, starting at 0, 0, and then going over 1, up 1 to get to the next point, it's got to go up half as far. And so it instead is going to be going up only a half when it goes over 1. And then, like normally, instead of going what I'd normally do of going over 2, up 2, I'm going to have to be going over 2, but up half as far. And half of 2, of course, is 1. And if we keep plotting points like that, we end up with this as our graph. Notice our graph is actually squatter. It's like we put a big weight on the top of our graph and compressed the entire thing. It wouldn't really make sense to say that it was stretched because we are not pulling it outward. We're actually squishing it and compressing it down. And for that reason, we call this a vertical compression by a factor of 1/2 instead of a vertical stretch, because stretching tends to make something bigger, compressing tends to make it smaller. And so anytime this number here is less than 1, actually I should say between 0 and 1, then that is a vertical compression. Anytime that number is more than 1, then it is a vertical stretch. And so with that in mind, you should now be able to tackle something as complex as this equation and go ahead and make that graph. So go ahead and just take a moment before I walk you through it and see, can you see exactly how this graph would lay out on your own? All right, so let's go ahead and actually now do this one. So first up, I'm going to always want to put my vertex at the point where the shifts have moved the vertex. So the +6 is going to move everything to the left 6. The +2 will move everything up 2. So my vertex is going to be right here at -6, 2. Now all I have left to deal with is the -2/3. The negative, as I know, means that it's going to be opening downward instead of opening upward. The 2/3 is what I'm going down and over by instead of 1 and 1. So let's actually take a look and see exactly what that means. So instead of going over 1 down 1, I would go over 1 and down 2/3. And then from that point, I would again go over 1 and down 2/3. And then from that point, I would go over 1 and down 2/3, which gets us to a nice pretty whole number again. And now to kind of build a bridge, you'll notice what we did there. We went down 2 and over 3. What's the slope of that part of the graph? -2/3. This is actually why slope is slope. Slope, that we've always called slope when we're dealing with lines, is actually just a vertical stretch or a vertical compression by whatever that factor is. It's just when we're first learning about graphing, we don't want to mix everyone up by calling it a vertical compression or a vertical stretch, so we just call it slope instead. But this idea of slope transfers very easily to the vertical stretches and vertical compressions like this. All right, the one thing I do want to note about that though, is that when we talk about slope, we can do that when the graph is straight. So for instance, if I keep following that particular pattern on this graph, notice it is straight on both sides because the absolute value graph is a V. However, later on when it's a curve, the vertical stretch and vertical compression will still have the same effect, but it will no longer be appropriate to talk in terms of slope because it changes, because slope only applies if it is straight all the way through. Okay? So just keep that in mind as we start looking ahead, because that's going to be one of the next things you see when it comes to these vertical stretches and compressions, is we will be applying it to a curved graph rather than something that's as straight as the absolute value like this.